Okay, folks, I can see we just hit 1 minute after the hour, so I'm going to go ahead and get started. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you're going to have the ability to submit questions via the chat window or to use the raise your hand feature in conjunction with your microphone and video camera. But we're going to wait to do questions until the end of today's presentation. So if you're not intending to speak in the meantime, please just do the best you can to make sure your microphone is muted and your video camera is off. It's my pleasure today to introduce Jonathan King. Jonathan is a Mendenhall postdoc at the USGS here in Golden at the Landslide Hazards Program. He completed his PhD in climatology at the University of Arizona in 2022, where he specialized in paleoclimate data assimilation. And since moving back to Colorado, he's been enjoying climbing and running in the Rocky Mountains. And so, Jonathan, thank you so much for joining us. I'm going to go ahead and turn it over to you. And just a reminder to unmute yourself.
All right. Well, thanks so much, Matt. Thank you, everyone, for being here. Like as Matt said, today I'm going to talk about some of our work over the last year and a half, building out an operational framework for post-fire debris flow hazard assessments. Oops, can it change? There we go. And so just for a little outline of the talk today, I'm going to start with a little background about post-fire debris flows and what these hazard assessments look like. And then I'm going to look at how, at the USGS, how we've historically done those assessments. And that's kind of setting the stage for the final section, where I'll talk about some of my new work, building out this new operational framework. So post-fire debris flows, what are they? I mean, it's kind of in the name, but these are debris flows that are happening after there's been a wildfire. And they can be very, very destructive. They'll damage property, they can destroy infrastructure like roads, and they can be deadly. And they're often triggered by rainfall in a way. To see why this is, I think it's useful to take a look at a burned landscape. So as you can see here, much of the vegetation has been burned off. So roots that may have helped to stabilize the soil might be missing. Leaves that would have been protecting the hillside from falling raindrops, those have been removed. And the hillside is covered in ash, which can help to mobilize flows. And kind of as a result of this, these burned landscapes are more susceptible to debris flows, particularly when there's rainfall. So in response to this, the USGS puts out these post-fire debris flow hazard assessments. This is an emergency USGS product. And what they do is they estimate the hazards given different rainfall scenarios. And so this map here on the right is showing the locations where we've done these assessments over the last few years. And this is just to show that we're doing quite a few of these. Specifically, we're doing over 50 assessments per year. This year we had a new record. We're at 95 or more assessments. The previous record was in 2020 when we did 82 assessments in 1 year. And one thing that's kind of important to keep in mind is these are often kind of coming in a big clump all in fire season. We're not doing one assessment each week all year, but instead we're doing 25 assessments in 2 weeks or more. So if we were to zoom in onto one of those dots from the last image, this is what we might see. This is an example of one of those assessments. And so what you'll see here is a set of colored polygons and then some also colored like line segments within those polygons. And so the polygons are showing you hazard assessment results for kind of catchments in a burned watershed. And the line segments are showing you results for the individual stream segments. And so this map here, this is kind of the main map that we release. This is a combined hazard map. It's a classification 1, 2, 3, 4. 1 is your low hazard, 2 is moderate, 3 is high. And this hazard score is going to take into account both the likelihood of a debris flow happening and then also the volume of sediment that would be mobilized if a debris flow were to occur. I'd say probably like 95% of our users are probably using that combined hazard map, but we do also release maps for the component models. So for example, we'll have a map that shows the debris flow likelihoods, we'll have a map that shows the volumes, And we'll also release maps that show the amount of rainfall that would need to happen to have a high likelihood of a debris flow. And some of our more advanced users will use some of these component model maps. For example, I believe the Weather Service uses the rainfall thresholds to help decide if they need to do a emergency notification. So how do we do these assessments? I don't think we need to go into the math behind any of these models, but I thought it would be useful to just do a kind of an overview of the ingredients here. So kind of in brief, there are three key ingredients to an assessment. These are topography data, soil data, and fire severity data. So the topography is going to tell us things like how steep are the slopes and where is water going to flow in this landscape. Soil data is going to tell us how prone the area is to debris flows in the first place. And fire severity data is going to tell us how perturbed the landscape is. And all three of these data sets, they're fortunately kind of publicly available. So when a fire happens, we can go in and grab these data sets and throw them in the model. And that's how we end up with one of these assessments. And just again, to emphasize that we're doing many, many of these assessments each year. So there's kind of our background on what the assessments look like. And now I'm going to shift gears a little and talk about how historically we produce these assessments at the USGS. So the first assessment that I could find a reference for was in 2003. And for kind of the first decade here, these assessments were done in a manual way. And I wasn't here then, but I've been told that it was very labor intensive and involved clicking through 1,000 ARC menus. But we didn't really have a way to release the assessments in this early stage. And so we relied on USGS open file reports to get the results out to the public. And so this here is an example of one of those open file reports. I believe this is actually the last one we did for a post-fire debris flow. But an important point about these reports is that they required peer review. And if you think about it, a fire happens and you do your assessment, but by the time that you've gone through peer review and there's been copy editing and the report itself gets published, well, this can be a fairly long time after when the fire actually finished. And so we had this very slow turnaround. Using this report here as an example, the fire was contained in May of 2013, but the report was published in January of 2014. So over half a year delay, which isn't the greatest for emergency assessments, but maybe stretching the definition of emergency there a little. Yeah, but kind of as a result of these challenges, we were doing a really limited number of these assessments each year, 10 or less, and actually in most years it was 3 or less. Now, things changed then in 2014, kind of in response to two big developments. So the first development was this new web interface that we developed to release these hazard assessments. And so what this meant was that we didn't need to do any more open file reports, and so we could have a much, much faster turnaround. Another advantage of the web interface was that it's much easier for the public to use. If you ask a random person on the street, what's a USGS open file report? They probably don't know, and they definitely don't know how to find it. But most people can use a web browser. The other thing that happened in 2014 was the development of this new codebase by Dennis Staley that implemented these assessment models. And so this was a collection of Python scripts, but kind of the key points here are that it was much less labor intensive, and we can now generate assessments in a few hours, which is a really big improvement. So kind of as a result of these developments, we saw a really huge surge in demand for these assessments over the years. Because it was so much easier to access, we had many more people looking at them and requesting that we do assessments in their areas. And that's kind of what led us to where we are today, where we're doing over 50 assessments each year. So I'm now going to kind of focus in on that old code base a bit. largely because it's been my job to try to improve it over the last year or so. And I will say, I'm going to kind of focus on issues and problems with that old code base today, but I really do want us to emphasize that this code base was a huge improvement for its time. It was very good that it was written, and it's a huge part of why we saw this surge in demand and that we're now able to do so many assessments. A lot of the issues with the old code base relate to the fact that it wasn't really intended for these large-scale operations that we are doing today. So the old code was written at a time when we were doing like 3 assessments in a year and not 20 assessments in a weekend. So in a lot of ways, it's the victim of its own success here. So just a few little characteristics of this old code base. It was a collection of Python scripts, quite long, several thousand lines of code. It relied heavily on Esri's ArcPy library, and it's what I would describe as a reference code base. And what I mean by this is this code was written to carefully follow the steps that were laid out in a series of scientific publications. And it does that very faithfully, but it perhaps wasn't optimized in the way that you might expect other kind of computational libraries to be optimized. So kind of going to start looking at some of the issues here with that old code. We'll start looking at some performance issues. The first thing is that it's fairly slow. 3 to 4 hours to run was a huge improvement over the old manual method, but it's still fairly long for a code to be running. One of the things you'll run into is fires will often arrive in clusters kind of right around fire season. If an assessment takes 4 hours to run, you can do 2, maybe 3 assessments in a day. But if 15 fires happen in the same day, you kind of have to get into these tricky questions of which fires do I prioritize? What am I going to run first? The other issue with the runtime was that testing settings for the assessment was fairly time consuming. So if I had my my sediment volume model, and I wanted to adjust one of the parameters and see if that gave a slightly better result, well, that was going to be fairly expensive to do. It was going to take another half a day to do that new run and see how the results changed. And so this meant that we were more or less fixed into whatever settings we started with. It was hard to change model parameters. Second issue with the old code was that it was prone to crashing. And in particular, this was for large megafires, looking at hundreds of thousands of acres. And the real issue here was just that the computer would run out of memory and it would die. And so, for example, we were, I believe, never able to actually run the Dixie Fire in its entirety. It's at around 1 million acres. I believe at the time they got around this by splitting that fire into several different domains and running each domain's assessment on its own. But it would have been nice if we could just put it all into the code and run. Okay, another kind of performance issue here is that the old code was rather inflexible. As I mentioned, it was a very long script, and so you might have lines in the code that are, depending on lines, hundreds or even thousands of lines earlier. So very hard to keep track of and difficult to adapt and change the code for new research. A kind of final problem here was that it really only worked for the US. You couldn't use it for international applications. And so, one example where this was a problem, in 2021, we had a collaboration with Greece where we were going to run some hazard assessments for them, and we just simply couldn't run the old code on it. And we had to do a more kind of limited manual assessment for that. Another set of issues here have to do with the availability of the old code. So the first problem here is kind of that the old code is not open source. Like I said, it relies on that ArcPy library, which is proprietary. So only people who have an Esri license could actually, run the code. And if for some reason we ever lost our Esri licenses, that's it, dead in the water. Another issue is that the code wasn't publicly available. Because it was such a long script, it was borderline impossible to do a software review for it and release it. And so it kind of remained this internal black box code, which isn't good for open science. We'd like our codes and our models to be publicly available. This next one's huge. It was the old code was really fragile. It wasn't version controlled, and any time that ArcPy would issue an update, it would break everything, and there would be a mad scramble to try to fix it and get it running again. And so, just anecdotally, when I started working here, it only ran on, I think, one computer. Maybe there was a second computer, and the understanding was that, if you were on that computer, you did not connect it to the internet if ArcGIS was open, because it would update ArcPy and that would be the end. The operational system is gone, and that's wild. Yeah, and so the last kind of point here is that the old code base was undocumented. Like I said, it's several thousand lines long. There aren't really any comments in it. And yeah, I did a read through of it when I started working here, and it took several months to really understand what was going on, which, more or less makes it a black box for most users. So there's kind of the background. This is where we were about a year and a half ago. And now I'm going to talk about some of my work building this new operational framework to kind of improve upon this old code base. And so kind of at the core of what I'm going to talk about here are three new tools. They're called pfdf, wildcat, and ocelot. And these are all Python packages, and they follow a modular design. They all build off of one another. And so this lets us design different tools for a variety of different users and different use cases. So yeah, here's our three tools, and I'm gonna walk through each of them in turn here. So starting off with pfdf. pfdf is really kind of the cornerstone of this new operational framework. It's a Python library with a collection of postfire debris flow routines. Yeah, and we're really going to use it as the foundation to build out these other tools. So some characteristics about pfdf. The first thing is that it's a Python library. It is not a script, but it's instead a collection of common small routines that you can mix and match and ignore and use however you like. You can combine it with other codes. You can use it to develop different types of hazard assessment workflows. So pfdf is really intended for Python users. And the real target audience here are researchers who are interested in developing new models and experimenting with different hazard assessment frameworks. So kind of going to compare pfdf to the old code base. So as I said before, we kind of had these performance issues, and now we'll look how pfdf compares. First off, pfdf is quite a bit faster than the old code. I've optimized it for speed. So kind of as an example here, the Cameron Peak fire is at about 250,000 acres. On the old code base, it took somewhere between 4 and 6 hours to run. And with pfdf, that assessment takes 5 minutes and 30 seconds. When the improvement holds for smaller fires too. Even a smaller fire would take between 2 and 4 hours with the old code, but pfdf can almost always do them in under a minute. And so one thing that's nice about this is, one, it's faster. We can run a bunch of fires in one day, but also it's much easier to play around with different model parameters and settings. If I want to tweak a parameter, I have a minute to spare, it's fine. I'll tweak that parameter and see how the assessment changes. Second thing about pfdf is it is more stable. Another thing I've optimized it for is to conserve memory. And kind of, the big payoff here is that it doesn't crash when you're analyzing large megafires. I'll say we've used it to successfully run the Dixie fire just to see if it could. And yeah, it was fine. pfdf, because it is a library, is modular. Everything in there is optional. You can use what you want. You can ignore what you don't want. You can develop your own codes and use a little bit of pfdf and then a little bit of your own code. Yeah, it's very flexible. And so kind of because of this, we've already been using pfdf to support new research and new codes. So kind of some examples here. Andrew Graber has a really neat study out recently about updating assessments as vegetation recovers from year to year. I've done work examining how we might implement large-scale pre-fire assessments. And I know Katie Barnhart has used pfdf to help support some new runout modeling codes. So here's just like a little snapshot from some of the research I was doing on the pre-fire assessments. This is a pre-fire assessment for the Pikes Peak region. The idea here is to try to estimate hazards before a fire has even happened. And we don't really need to go into any details here, but I just wanted to point out this is a large area at 500,000 acres. It's using an experimental framework, and the code runs just fine. The last kind of performance advantage here is that pfdf is international. It's bring your own data. It's not hard-coded to anything. And so we've already used it this year to do several international assessments. For example, these 4 assessments in Canada. And then kind of looking at the availability of the code base, pfdf is open source. It's all Python. If you have a computer, you can install Python and you're good to go. You don't need a license or anything. pfdf is also publicly available. I've showed a couple links of it so far. I'm sure there will be another one again, but it's available on code.usgs.gov. It has a citable DOI, so you can use pfdf for a scientific publication and cite your sources. And you can also install it using standard tools. So if I have any Python users out there, you can do a pip install to get pfdf. pfdf is also a lot more robust than the old code base. It's all version controlled. It runs on any operating system, and all the stable releases are tagged. So if the code breaks, or if you just dump a mug of coffee on your computer, it's fine. Just get a different computer, install the last stable release, and we're up and running again. And then the final point here is that pfdf has very comprehensive documentation. That link at the bottom there will take you to the documentation page, but this includes things like a user guide where we introduce the various models that we'll be using. There are tutorials that show you how to use pfdf to do different types of analyses. And there's an API, which is a reference guide to all the different commands and options that are in the toolbox. Yeah, and so that's pfdf. You can find it at this repository here. So like I said, pfdf, we're going to use it as the foundation to kind of build out these other tools. And so kind of the next tool that we're going to look at here is wildcat. And so wildcat is a command line tool that is going to implement USGS style hazard assessments. And kind of comparing it with pfdf, you are locked into doing a hazard assessment when you use wildcat. So in that way, it's less flexible than pfdf. You need to use our assessment framework. But kind of because it's more specialized, it's also much, much easier to use. And so wildcat is really intended for practitioners. If you want to create a hazard assessment and release it, this is the tool I would recommend for you. And yeah, again, much lower barrier to entry. You don't need to know Python, and it's a much simpler toolbox overall. So kind of at the core of wildcat are these 4 key commands. There's the initialize command. This just makes a folder on your computer that'll kind of store assessment results. There's a preprocess command. And what this is used for is to clean up data sets before you do an assessment. So for example, it's really common for you to have a number of data sets, and every single one of them will be in a different map projection. And also some of them will have data artifacts in them. And so this command will just take this varied real world data and clean it up and get it ready to go. There's the assess command. This is the command that actually runs a hazard assessment, ideally on these pre-processed data sets. And then there's the export command, which is going to export your results to GIS formats like shape files and GeoJSON. So just kind of doing a little comparison of pfdf and wildcat. Wildcat is built using pfdf, but again, it's going to be a bit more focused in what it does, and it's also going to be easier to use. So on the left here is an example of some pfdf code that you could use to pre-process a bunch of input data sets. And this is kind of the identical code using wildcat. It's just one line. You open up a command prompt, type in wildcat preprocess, hit enter, and you're good to go. Again, kind of a similar comparison for running an assessment. If you want to run a USGS style assessment using pfdf, you're looking at maybe about 100 lines of Python code, whereas with wildcat, again, it's just one line, type it in, hit enter, and you're good. Yeah, and so those are the 4 commands. And I will say, we're planning to do rolling releases of wildcat, and we'll plan to add in more commands here as the project matures. So, eventually we might add in some commands that will compute statistics over the network, or, create PDF maps, or, other nice conveniences. Now, one thing I want to say about wildcat, although you're locked into a USGS style assessment, we're trying to keep it as flexible and as general as possible still. And so all of these commands are configurable for each assessment you do. So when you run a wildcat assessment, that assessment will get its own configuration file, and it'll have a number of parameters in there that are used to design the stream network, and also modeling parameters. So if maybe you want to run the volume model with a different confidence interval, you can totally do that. You have to calculate a confidence interval, but it's flexible in what you're allowed to do. And I'll just say, again, each assessment gets its own configuration file, so you're not locked into having one specific configuration for all the fires that you run. Like pfdf, wildcat is documented. Similarly, it has a user guide that's going to explain, this is how we design a stream network. These are how the models work. We'll have a tutorial for running an assessment. And it likewise has an API that walks through all of those different configuration parameters. In terms of public availability, it should be publicly released very, very soon. The initial release, it's complete. We've submitted it for release, so we're just waiting for center approval, and it will be public. Yeah, and if anyone in the audience, if you're out there and you think you'd like to try running wildcat, feel free to shoot me an email, and I can notify you when it is released. Okay, so that's wildcat. And the last kind of new software tool we're going to look at here is Ocelot. And this is our in-house operational code base that we're using to actually run the assessments that get put on that web interface. Ocelot is very, very similar to Wildcat. It does pretty much all of the same things, but it also includes 1 or 2 extra files that help support this web interface. And so Ocelot is live. We've used it to run over 95 assessments this year. It's a new record. We've done international assessments. It handles complex topography very well because we can go in and change those parameters in the configuration file, and also because it's so fast that it doesn't take too long to test out different parameters. And also it doesn't crash for large megafires. Right now, Ocelot is built on top of pfdf directly, and that's because pfdf is publicly available. But we're planning to migrate it to Wildcat as soon as Wildcat is publicly released. Yeah, so there we have it. This is our new assessment framework, is these 3 software tools. Kind of going forward, our next steps here, we'd like to take some time and try to update our web interface and make it more sophisticated. The web interface was kind of built at the same time that the old code base was, so it kind of inherits some ideas from that old code base. So one of the things we'd like to add the ability to do is to display results for different rainfall scenarios. The old setup was kind of locked into one specific design storm, but kind of looking back at that configuration file here, one of the parameters you can put in here are different rainfall intensities that you want to model for. And since we can model multiple intensities, it would be nice to put them on the web interface as well. Another thing we'd like to add to the web interface, I mentioned that Andrew Graber was doing work on how to update assessments as vegetation recovers. And so we'd like to add the ability to show this is the assessment for year 1. Okay, now it's been updated because it's year 2 and the vegetation's recovered. And this is how the assessment has changed. So those are kind of some of the planned changes to the web interface. For pfdf, we'd like to add some tools to download common data sets. As I said, pfdf is bring your own data, and it'll always be bring your own data. We want to keep it general and flexible, but we'll also acknowledge that there are certain data sets that people use over and over and over, and so it'll be nice to make it a little easier to just grab and download some of those. Some final planned updates are for Wildcat. I think I mentioned this already, but we'd like to add in some commands to do statistical summaries over the network, and maybe some commands to make PDF or JPEG or PNG maps that, if you have downstream users who want to look at the assessment, but they're not used to shapefiles, great, you can send them the PDF. Yeah, and I think I finished a little early here, but can move into some questions.